called the standard molar enthalpy formation. This is to say, because the absolute value of H is not well defined for a system, we cannot immediately give you a number to say what is the total energy, total H of this state, and this state. If we know that, it will be easy to do math to figure out the delta H and things. But it's not well defined because we're not creating anything out of nothing. It's just relatively tricky. Because of that, we do not talk about, again, an absolute value of H. We talk about delta H. And this delta H, in this case, corresponds to the change of the enthalpy for the system as it goes from the pure element state into a particular compound state for the different chemical compounds you are looking at in a chemical reaction. That is to say, we define the relative H based on the pure elements as a reference form. And then we say the delta H of the change of essentially the heat of constant pressure from the pure elements to the particular species you are looking at, based on either direct measurement or the indirect calculations, we take that number as the standard molar enthalpy of the formation, and we write it as delta F, meaning the formation of H under the standard condition, again 1 atm. Also, it's written as delta H circle F. You can either way is fine, just different people. Both notations actually differently used. They are the same thing. So this is to say, if we can always refer all the energy states of everything back to the pure element state of those elements, we have a way to define the H for everything, and we can look up a table for those different values of the different chemical species. So for this to work, the basis is actually to say all elements are conserved in chemical reactions, and there are no nuclear reactions, because nuclear reactions change chemical elements. That's not discussed at all. So assuming there is no nuclear reactions, and you always conserve the same elements in your system, and because of that, you can always refer to the pure element state of the same elements in your chemical reactions without any trouble. So you can always refer to a particular element state. And in that case, when we say the delta HF is just assumed to be 0 as a reference state for a pure element in its reference state. So the pure elements, we'll talk about the reference state more later, but for now we can say pure elements is essentially given a number of 0, and every other thing is referred to that 0 as a reference point. So if that's the case, then it's actually relatively straightforward to calculate the delta H for a given reaction based on the known numbers of the different chemical state of the species, and we always have the formation and enthalpy. That is to say, if we look at this particular type of generalized chemical equation, A mole of A plus B mole of B to react generate C moles of C and B moles of D, then the entire change of delta H is essentially mathematically C times the molecular formation enthalpy plus D times the of that HD, essentially, and minus the A times this and the B times the delta FH of the B. This is to say, everything is on the reference state, but CI essentially does not care. If you go through the derivation of the mathematics, it actually can show, you can imagine that you can dissociate everything first back to the element state. So everything you can imagine is dissociated into a pure element form. And then you reform the final product from those pure elements. However you mix up those things, how you do this process, because they are state functions, it doesn't matter. They are always well-defined energy for a particular state of a particular compound, and because of that, you can always go through those type of calculations easily to figure out the delta H for any given reaction by knowing the formation